This video covers Module 3, Part 1. Please make sure you're completing the guided notes for this section along with the video. And in this video, we're going to cover solving systems of linear equations using substitution. So a brief introduction into systems of linear equations is when we're given two or more linear equations, we call this a system. And today we're going to focus on solving them using substitution. So I've been given a line and another line. Right, so here's my first line. I'm recording from home today, so that's my cat, if you can hear the meowing. And I'm given a second line, right? So a solution to a system of linear equations are the ordered pair or pairs, right? It could be plural, that satisfy both equations. So for example, if I had these two linear equations over here in blue and orange, they intersect right at this point. This ordered pair, whatever it is, would be the solution to that system of linear equations. If two lines intersect, that's when they have one solution, just like in this example over here. If my two lines are parallel, they're going to have no solutions because parallel lines have the same slope. They just have different y-intercepts. They're never going to intersect. And if two lines are the exact same line, meaning I'm given an equation for the exact same line, those are never not touching each other. They're the same line. So that means that every single point on the line is a solution. So there are infinitely many solutions, specifically every single ordered pair, however many of them there are, which are infinitely many of them on that line. So first things I want us to talk about are solving a system of equations by substitution. And like I said, we're going to get three different types of solutions. First option's one solution. Here's kind of a visual of that. Second option's no solutions when my lines are parallel, and infinite solutions when my lines are the exact same line. They're on top of each other. So we've used substitution before to solve problems, for example, those perimeter word problems. But the first step that we're going to do is pick one of our equations and get the variable by itself. We need to isolate the variable. We could then substitute our expression from step one into our other equation. So we've got two equations. Into our second equation is what we're going to substitute into. That should give us an equation in one variable, and we can solve. Then we would substitute what we find in step two back into the equation from step one and solve. Now we have our two answers, our x and our y, and we would write those as an ordered pair. So let's do a bunch of examples to make sure we feel really confident solving these types of problems. So for our first example, I have 5x minus 4y equals 9 and x equals 2y minus 3. So what I'm going to do is I already have an equation solved for a single variable. I know that x is 2y minus 3, and I'm going to go ahead and substitute that into my top equation. So I'm going to have 5, but instead of x, I'm going to write 2y minus 3 minus 4y equals 9. And now we have an equation in a single variable. I know how to solve this. The first thing I'm going to do is distribute. 5 times 2y is 10y. 5 times negative 3 is a negative 15. Minus 4y equals 9. Next, I combine like terms. 10y and 4y give me 6y minus 15 is 9. I add 15 to both sides. 6y is 24. Divide both sides by 6, and y equals 4. That took quite a few steps, but it's a tool we already had in our toolbox, solving an equation for a single variable. So I have y equals 4. I now can plug that in to my original equation in order to solve for x. So I'll take this, and I'll have x equals 2, but instead of y, we're going to plug in 4 minus 3. So x is 8 minus 3, so x is 5. That tells me that these two lines intersect at the ordered pair of when x is 5, y is 4. This is my answer. And one way I could check that is if I substitute this point into both of my equations, I'll get a true statement. That's a good way to check your answer if you're ever unsure. For this second example, I don't know why all my math went away. I've got 3x plus 4y equals negative 4 and x plus 2y equals 2. Well, isn't that exciting? I can go ahead and solve this bottom equation. I'm going to solve it for x. And I could have solved either equation for x. I could have solved either equation for y. This bottom equation already has a variable by itself, so it makes my life a lot easier. I'm going to subtract 2y from both sides. I've got x equals 2 minus 2y. That's my new equation, and it's equivalent to what I had before. I can now substitute this in for x in our first equation. I'm going to substitute it in here. So I would have 3 times 2 minus 2y plus 4y equals negative 4. And I can go ahead and distribute 6 minus 6y plus 4y is negative 4. I combine like terms. 6 minus 2y is negative 4. I subtract 6 from both sides. Negative 2y is negative 10, so y is going to be 5. I then substitute that back in to one of my original equations. I don't want to substitute it into the one I solved. I don't want to do that because if I made a mathematical error, I won't be able to catch my mistake. So now I have x plus 2 instead of y. We're going to have 5 equals 2. X plus 10 equals 2, so x is negative 8. So my answer is that these two lines intersect at one point, and that point is when x is negative 8 and y is 5. For example 3, again, losing my equations, I've got 5x plus 5y equals 20, and x plus 4y equals a negative 14. That's what you guys should have in your guided notes. So I'm going to go ahead and solve this bottom equation for x by moving 4y to the other side. So I have x is negative 14 minus 4y, and I'm going to substitute this in for x in my top equation. So I have 5 times negative 14 minus 4y plus 5y equals 20. We distribute 5 times negative 14 is a negative 70 minus 20y plus 5y is 20. I combine like terms. I move my constant to the other side. I find that y is negative 6. And now I can substitute that back into either of my original equations in order to check my answer. I'm going to plug it into the second one, into this one, right here. So I have x plus 4 times negative 6 is negative 14. X minus 24 is negative 14. X is going to be 10. So these two lines do intersect, and the solution, the answer, the point where they intersect would be when x is 10 and y is negative 6. For our fourth example, I have y plus 1 equals 5 times x plus 1 and y equals 5x minus 1. I've already solved this for y, so I can substitute this in. I've got 5x minus 1 plus 1 equals 5x plus 1. Sorry, 5 times x plus 1. We distribute on the right-hand side. We combine like terms on the left. I get my constants together, and we notice something, right? My constant, not my constants, my variables. My variables cancel out. So I get 0 equals 5. This is a false statement. And before, when we were solving equations and got a false statement, that meant that there were no solutions. And the same is true in this case. There are no solutions, and there are no solutions because our lines are parallel, meaning they have the exact same slope. They never intersect. So this example has no solutions. Next, I have y equals 3 minus 2x and 4x plus 2y equals 6. I've already solved this first equation for y, so I can just go ahead and substitute that in. 4x plus 2 times 3 minus 2x is 6. 4x plus 6 minus 4x is 6. I combine my like terms, 4x minus 4x, that cancels out. I get 6 equals 6. This is a true statement. And before, when we were solving equations and we found a true statement, that meant that there were infinitely many solutions. Infinitely many solutions, right? That means our lines are the same. They have the same slope, they have the same y-intercept, they are on top of each other like this. So infinitely many solutions is correct, but if we want to be specific, our solutions, and we should want to be specific, are every single ordered pair such that they meet the criteria of either of these equations. I could either write this equation, which is in standard form, or this one, which is pretty close to slope-intercept form. I'm going to pick the top one and put it in slope-intercept form. And that's my personal preference, putting it in slope-intercept form, because then I can say, okay, this line has a y-intercept of 3 and a slope of -2. It's really good for us to visualize what's going on with our linear systems. So our last example using substitution is going to be a word problem. I know everyone is so thrilled. So the first thing I want to do is look over the problem. So Ted and Ricky are throwing a party and wanted to buy toasted ravioli and hot wings. So toasted ravioli, if you're not from St. Louis, is actually pretty darn good. You should try it sometime. Costs $7.50 per pound, and hot wings cost $6 per pound. And together they bought 12 pounds. And the total bill was $79.50. So I'm trying to figure out how many pounds of each did they order. So some good variables, I think, would be R and W. So I know that that'll stand for the pounds of TRAVs and the pounds of rings. So I know that together we had 12 pounds. The bill was $79.50, and my ravioli cost $7.50 a pound, and my wings cost $6 a pound. So this top equation, I could solve for either R or W. I'm going to go ahead and solve it for W. So in order to do that, I subtract R from both sides, and I got W is 12 minus R. And the reason I did that is because I know W is going to be multiplied by 6. I wouldn't have to deal with a decimal. So I can substitute this in for W. I have 7.5 R plus 6 times 12 minus R is $79.50. Don't forget we're working with money right now, but when we solve for R, that's going to be the pounds of ravioli. So 7.5 R plus 72 minus 6R is $79.50. We combine like terms, and I have 1.5 R plus 72 is $79.50. I move the constant over. I get 1.5 R is $7.50. Plug that into my calculator or do it in our heads, and we find that R is 5. So we got 5 pounds of ravioli. So if I got 5 pounds of ravioli, how many pounds of wings did I have? So I look back at our original equation, which was r plus w is 12. This r looks kind of like a p. And I can substitute in 5. So 5 plus w is 12. Move my constant over, I find that w is 7. So there were 7 pounds of wings at the party and 5 pounds of ravioli.